Hello everyone, let's talk about another medium problem on Leetcode today. Find the minimum and maximum number of nodes between critical points. Leetcode 2058. A critical point in a linked list is defined as either local maxima or local minima. A node is local maxima if the current node has a value strictly greater than the previous node and the next node. Similarly, a node is a local minima if the current node has a value strictly smaller than the previous node and the next node. Note that a node can only be a local maxima or minima if there exists both a previous node and a next node. The nodes at the head and tail will not be counted as local maxima or minima. Then, given a linked list head, return an array of length 2 containing minimum distance and maximum distance, where minimum distance is the minimum distance between any two distinct critical points and maximum distance is the maximum distance between two distinct critical points. If there are fewer than two critical points, return -1 and -1. In example 1, there is no local maxima or minima, so we will return -1, -1. In the second example, let's go to my blog. Let's see this linked list here. So we can see that there are two minimas, 1 and 1, because 1 is less than both 3 and 2, right? That is both previous and next element. Similarly, 5 is maxima, right? Because 5 is greater than its previous and next node, which is 2 and 1. So that's why it's a local maxima. So we return 1 and 3, and the reason is the minimum distance between two critical points, that is 5 and 1, is actually 1 here, right? Similarly, the maximum distance is between these two ones, which is 3. So we will return maximum distance as 3. So we will return 1 and 3 as an answer. Now that we have seen the example, let's see how we can actually solve this problem. So one way can be that we actually traverse the list twice. So in first pass, we actually go through the linked list and add the position of these critical points in the new list. So for example, position of 1 is 3, then position of 5 is 5, then position of 6 is 6, right? So the list will be 3, 5, 6 because those are the only three critical points. And it's also sorted, right? Because we are moving from left to right and just adding the positions. So the maximum distance will be the difference between the last position and the first position. So in this case, it will be 6 minus 3. So it will be 3. So that's the maximum distance. And for minimum distance, we have to again traverse through this list between two adjacent elements and see what is the minimum. So distance between first one and 5 is actually 2. So this is initial minimum, but then we see 5 and 1. And the distance here is just 1, which is actually less than our previous minimum equal to 2. So now 1 becomes our minimum. Because now there are no positions remaining in position list, so we will just return 1 as minimum and 3 as maximum. So this is one way, and in terms of time complexity, it is O of n because we are going through all the elements in the list once. And in terms of time complexity, actually it's really good solution. But now the question is, can we do it in one pass? And the answer is yes. So for that, let's revisit our first solution. If we look at the positions of our critical points, it is 3, 5, and 6, right? And for the minimum distance, do we actually need to store position of all the critical points in the list? And the answer is no, because all we care about is two consecutive critical points. And we calculate the distance between them and see if it's actually minimum so far. If it is, then we update our minimum distance. Otherwise, we will just continue and find next critical point. So for minimum distance, we don't have to store any list or anything. Similarly, if we look at our maximum distance, and suppose we are traversing through this list only once and we have the position of this critical point. So for maximum distance, we only care about the first position, right? So we have to store it somewhere, and then we can always calculate distance between the current point and the first point. So this will always give us a maximum distance, and we will keep on updating it till we actually reach the end. So now let's see it in action. So this is our linked list in the second example, and initially we will be given the head pointer, and I have marked all the critical points in green color. So when we first initialize, what we need is the previous position, because for minimum distance, we just need to calculate the distance between the previous critical position and current critical position, and then see if it is minimum so far. Similarly, we need to store the first position, that is position of the first critical point that we saw in the linked list, and position will be our generic pointer in the list, which will be just tracking what is the position of any node in the list. And if you remember, the condition for critical points is that for node to be a critical point, there should exist both previous and next node for it. So the head pointer and the last node cannot be the critical point. So we will actually start our position from head.next, which is node with value 3 in this example. So initially all the previous position, current position, first position will all be -1 and our position will be at 3. Let's call it position 0. Now we can see that node 3 is not a critical point because it is less than previous node and more than next node. So we will just continue and move our position to next node 1 and our position now becomes 1. So then we come to node 1 and we see it's a critical point. So we will actually mark it as our current position. And this will also be our first position because we saw the first critical point in the list and continue. Then we come to 2 and it is not a critical node. So we will just continue and go to the next one. Now we can see that node 5 is a critical point. So we will update our positions a bit. Current position will move to position. But before that, we will move our previous position to current position. And now we can actually calculate the minimum and maximum distance. So we can see that our previous and first position are at node 1, which is at position 2. And our current position and position are at node 5, which is position 4. So now our minimum distance is 4 minus 2, that is 2. And also because we have two critical points, also the maximum distance is also the same. So min and max will be 2 in this case. And now we go to the next node, which is 1. And we see it is a critical point. So we will move our current position to this position. But before that, we will actually move our previous position to the current position. And now we recalculate the minimum and maximum distance. So we can see that our first position is at position 2. Like 3 was position 0, if you remember. And our current position is position 5. And for maximum distance, we will take the distance between the current position and the first position. So it will be 5 minus 2 equal to 3. Similarly, now we will calculate the minimum distance. So for that, first we calculate the distance between the previous and the current position and then see if it is the minimum we have seen so far. If it is, then we will update our minimum distance to this value. The minimum distance will now become 1 because our previous minimum distance was 2 and this minimum distance is lower than that one. So we will update our minimum distance to 1 now and continue to the next node. And now we are at the last node of the list and we can see that this is not a critical point. And so in the end, we will just return minimum equal to 1 and maximum equal to 3. Now that we have actually seen this example, let's jump into the code part. So first thing we need to do is we actually define our previous and current pointers, right? Luckily for this linked list, head and the last pointer cannot be the critical point. So we can just take previous as head and this node current equal to head.next. And let's define our answer and define all our positions. So it will be dev position, current position, first position equal to -1 and position equal to 0, which tracks the position of the current node. And now we will start iterating on the list till the point current.next not equal to null. Generally, we check till current is not equal to null, but in this case, we have to check the value of the next as well as previous value, so they shouldn't be null. So that's why we will check current.next not equal to null and continue the loop till this point. And why we have to do it? Because for this condition that node can only be local maxima or minima if both previous and next nodes exist. So that's why. Now we check if the node is a critical point or not. That is by checking whether it's a local minima or local maxima. So first thing we check is if it's a local minima. So we can do it by checking if current.val is less than previous.val and current.val is less than next.val. So this is the first condition. Then we have to also find if it's a local maxima. So either of them will be like a critical point. So that's why we use the OR condition. Now, so if current.val is more than previous.val and current.val is greater than next.val, that is current.next.val. It should also be current.next. That means we have found our critical point, either minima or maxima. Then we just update our previous position to current position, set our current position equal to position. And if our first position is not yet set, that means we should also set it here. And now if our previous position is not -1, so that means we have found at least two critical points. Then we can actually calculate both minimum and maximum distance, right? If answer 0 is -1, that means minima is yet not set. So we will set it. So we will set it to current position minus previous position. Otherwise, we will calculate the distance between two adjacent nodes and see if it's a minimum so far. We can just set it using math.min of answer 0 and current position minus previous position. And in any case, we will just set our maximum because our position is always in the increasing order. And once we do that, we just go to the next node in the list, increment our position. So we will just do previous node equal to current, and current is equal to current.next. And once we do that, we just return our answer. So now let's run this code. Awesome. Let's submit this code. Cool. So in terms of time complexity, it is O of n, where n is the length of the linked list. And we are processing each node only once. So that's why it is O of n. And in terms of space complexity, we are not using any extra space. So it is O of 1. So this is just the one pass solution. So I've shared both the one pass and two pass solution on my blog. Please check out the link in the video description. I hope this video was useful to you. If it was, please like and subscribe. Have a nice time. Thank you.